Hello, I hope you are doing well. In this video, I will model as a reactor and tracer injection. So I select 2D and I select transport diluted species and laminar flow. I click on a steady stationary. So I select centimeter as a length unit and I draw a 5 centimeter with 20 centimeter height rectangle. I add water. So in this part, I define an inflow for mass transfer. It is inlet and this is outlet. So I define an outflow here. The inlet, the concentration is constant. The outlet, the concentration, the boundary condition is the normal vector of gradient of concentration is 0. So it is for mass transfer. I must define the concentration of inlet. So I will come back to this part. So for laminar flow, I select an inlet. I define 0.001 for inlet flow, and outflow or outlet, the pressure would be 0. I couple velocity profile with mass transfer because we have two kind of mechanism for mass transfer. The first one is diffusion, and so we must define diffusion coefficient between elements, and we must couple the fluid flow with mass transfer based on these equations. So it is our inflow. So I will introduce inflow as a function. I right click on definition function, and I can define a pulse or Gaussian function. So if I define this pulse function, I can use it for define the inlet of the reactor. So I click on inflow and I put I defined this because the name of this function is GP1, so it is the name of function. It is the independent variable in function, so it is time, and it must be unitless, so I put it 1 per second in the bracket. If I, for example, remove that, like this, it would be error regarding the unit. So it must be 1 per second multiplied with C0, and I will define C0 in parameters as 10 mole cubic meter. So it is our inflow. I mesh my system. So remember, because I defined a variable with time, so I must use time dependent study. So I add a study and time dependent. Before that, we must change the x-axis of direction, so I put 3 here. So at the time of 0, the false function will increase and then decrease in 6 seconds. So I define 10 seconds for our simulation, and I click on compute. So after a while and after running, we have our results here: velocity, pressure, and concentration. We can see the concentration profile for different times. If we increase the time, we can see the movement of this one. I can increase interval to 1 second, and that one to 100, for example. So we can see the results for different times. It's fantastic because you can track the phenomena of mass transfer. You see the middle part of the reactor. There is much more. The transfer is much more faster than near walls, because the velocity is more in near wall, in middle of the reactor or our tube. So it is the movement of that part. So I can drive an animation by clicking on this part, results, animation player. And it would be kind of pulse in our system. It is for injection of a tracer in a reactor. This phenomena used to investigate the ideality of plug reactors. Also, you can check and model your reactor difference from ideal plug reactor by this way. It is a well-known technique to investigate the behavior of the plug reactors, similar plug reactors.